Our next talk will be by Paul Nelson from Aarhus.
Yep. All right, thanks so much, Sound. Happy to be here for Peter's celebration. So I was Peter's linear algebra student 21 years ago. And we'll come back to that point throughout the talk now and then. So, that was not a joke, but thank you. Okay. All right, so where are we going to start? Well, we'll start with a topic that's familiar to many people attending here, which is the question of asymptotics of moments of the zeta function. So if we integrate the zeta function, say raised to the 2k power from 0 to t, there are, by now well-developed conjectures for how this quantity should behave. Should behave roughly like t times some logarithm power of t. And of course, this is a conjecture that is wide open, but it's known in a couple of cases. So it's been known for a while. So for instance, it's been known when k is equal to 1 by Hardy and Littlewood. And then when k is 2 by Ingham, going back to, I think, okay, now we got to write 19, don't we? Yeah, okay, it's been a while. Yeah, so the case k equal 2 is a particularly critical one because, so this one implies in particular, if you know the asymptotic formula written over there, that the integral of the zeta function to the 4th power is bounded by a bit more than t. We could refine that to a logarithm if we wanted to. And so it implies the convexity bound for the zeta function with a little bit more work. So it's a particularly critical case of this moment problem. For instance, if you're interested in bounding the zeta function using bounds for moments, because pushing k a little bit higher, which nobody has succeeded in doing, would improve this bound automatically. And also kind of fudging with the estimate a little bit, maybe inserting some weights, some amplification in the spirit of Duke, Friedlander, and Ivanich would also give a little bit more juice here and allow you to prove a little bit better bound. So this is a particularly interesting moment problem. And so one of Peter's early papers, so 1985 is when it was published, I think. So gave a geometric approach to understanding this kind of moment problem. So in his paper, he described it as kind of, in some sense, interpreting arguments of Titchmarsh in a slightly different vein, but it was kind of, as far as I know, the first work that really kind of put automorphic forms at the center of this whole story. So the main actor in that story is a function that I'll call phi. So this is the Eisenstein series for H mod SL2Z. And we'll take the one with trivial parameters. So it'll have a Fourier expansion that looks something like, so some simple function, so say y plus some multiple of log y plus the interesting part, which is, yeah, let's say a sum over non-zero integers of divisor function normalized a bit times, let's say, a Whittaker function wn of y, and then some exponential e of nx. So by virtue of the fact that the function tau of n appears as the Dirichlet coefficient of the square of the zeta function, this automorphic form has an integral enjoys an integral representation related to the square of the zeta function. So I'll be a little vague about what we mean by integration here. It requires a little bit of regularization because of these first couple terms up there. But so if you integrate phi along the imaginary axis multiplied by y to the, let's say, the it dy over y, then a simple unfolding gives that this is basically the zeta function squared up to some additional factor that you get coming from this this Whittaker type function. So it's a k0 Bessel function in this case, and the integral you get looks like w of y times y to the it dy over y. So so for instance, I guess when we first start studying the zeta function, we probably learn an integral representation for it that involves the Jacobi theta function, which would not give the square of the zeta function, but rather the zeta function itself. But I mean, this integral representation here is a perfectly valid way to develop the analytic properties of the square of the zeta function. And we should point to a couple features that make it useful for that purpose. So one is that you can actually evaluate this integral explicitly in this special case. So it ends up being maybe up to some factors of 2, just a renormalized gamma function. So it's the gamma function. So the subscript r basically means to divide the argument by 2, and it's the square of that. So this is kind of the product that then satisfies a very nice functional equation when we view this whole expression as a function of the variable t. And so if, for example, you wanted to understand the analytic continuation of the zeta function using some identity like this is a very useful tool for that, because the gamma function we know never vanishes. So that's kind of a fact that I guess I learned as an undergrad at some point. It doesn't vanish. So in particular, you can't have any zeros introduced from this factor that would compensate for a pole, assuming you know the analytic behavior of the left-hand side. And so it's a very useful expression for that kind of analysis. But if you want to do, say, some estimates involving an expression like this, so say if you wanted to bound the zeta function in this way, it's not very good to have a gamma factor on the other side of this expression, because, okay, while the gamma function is qualitatively never vanishing, quantitatively it comes quite close to vanishing. It decays exponentially as t goes to infinity. So this is not immediately a useful tool for estimating zeta. But okay, something that came up in Peter's paper was the following idea, which I think I'd like to write on one of the middle boards. So it's this basic idea that if you deform this integral representation, so namely take this quantity and replace it with phi of iy plus some real shift. So I'll call the shift argument t, and I'll just foreshadow that we'll take t to be something basically of the same size as t. So when I say t, I won't be too vague. And so then we get a new integral representation where, okay, on the left-hand side, we have that shifted version. And on the right-hand side, we again have the zeta function squared. But now the new integral has this additional additive oscillation. Which is kind of a convenient feature, because so, you know, if you look at the original expression here and you think of w as a fixed quantity and t is tending to infinity, so you know by integration by parts that this is going to decay rapidly. But here, you know, you can't really integrate by parts. If you tried doing a proper stationary phase analysis, you find there's actually a stationary point at something like 1 over 2 pi, or 2 pi maybe. So this integral by stationary phase analysis will be not exponentially small, but instead of size comparable to something like t to the negative half, which is quite a bit more manageable than exponentially small. Okay. And so to pass from this to a fourth moment estimate, one can apply Parseval's identity, which I think I'll keep here. So if we integrate this quantity squared, we can understand that in terms of the corresponding squared integral of its Mellin coefficients, which we can evaluate using the right-hand side. So this, I guess by the computation here, at the very least bounds from below, but in fact, I mean, we can understand it at least approximately as an integral over t of size comparable to t of the fourth moment of the zeta function. So what we get by squaring the square of the zeta function. How about the what? Yeah, I think, so I'm being very vague about what I mean by integration here. And so what I might mean more precisely is take phi, subtract off its constant term, view this as an analytic function of what I've called IT, maybe first define for its real part big enough, and then continue. Or another way to get around that subtlety would be to work with a cusp form. Yeah, but thank you. Yeah. Any other questions about? Okay. So I should also remark, the point of his paper was not to give a new approach to the fourth moment of the zeta function, but instead rather to kind of give an argument that's robust enough that it applies more generally without the complication that would otherwise ensue. So his paper actually addresses kind of the analogous question, but over general number fields, which, you know, when one approaches them using kind of the classical methods, one often encounters difficulties. So this gives a kind of very clean conceptual approach that avoids those. And I mean, I guess this basic, yeah, I guess this paper spawned a lot of kind of further work and reflections over the next couple of decades. I'll mention just a little bit of that. So, I mean, I don't know where this observation was published, but there's a very simple group theoretic interpretation of this argument, which is that if you lift the function phi to, let's say, GL2, so I'll use brackets GL2 to mean GL2R mod GL2Z, then after you've done that, you can interpret the quantity that we're integrating as, well, the lifted function evaluated at the matrices that I'll write here. Okay, where I guess I'll fit in up here the definitions. So A of y is a diagonal matrix, and N of t is an upper triangular unipotent matrix. Okay, so then this quantity here becomes simply, I mean, maybe I'll say this entire quantity here can be rewritten as an integral over the quotient of GL1 of the right translate of phi by the unipotent matrix n of t. So here this notation will always mean to translate on the right. And I mean, written this way, it's kind of an identity that extends to the extent of the theory of integral representations for the pair of groups GL2 and GL1. And you know, for instance, you can interpret everything starting with this left-hand side going to the right-hand side adelically and over number fields, not just when working with t-aspect twists. And so this was done quite a while later. So in this landmark work of Michel and Venkatesh, so their IHES paper called the subconvexity problem for GL2. So their paper, so it in particular gives a subconvex bound for GL2 over number fields in all aspects, but also over GL1. And there are two methods that kind of come into the paper, and one of them is essentially an adelic and more representation theoretic version of this argument, where so you interpret this quotient now not as reals mod integers, but instead as adels mod rationals, and otherwise you have kind of similar phenomena. And so, I mean, one thing they get from this is a subconvex bound for, GL1. So, again, over number fields and in all aspects. And as I said a bit earlier, you can also take phi to be a cusp form. So this gives a bit more generality. You can also do GL1 twists of GL2 forms. So if you're not familiar with automorphic forms and more general L functions, just consider this as kind of a remark. But yeah, the point is that, you know, this initial paper was kind of the impetus for some research a couple decades later that gave kind of a very general, robust result that I've indicated here. And so one of the one of the features that I haven't maybe mentioned on the top board yet is that so I mean the idea of varying the vector as kind of exemplified by this example, you can do it in more general ways than just by translating by a matrix. So for example, you can replace phi by its application under Heck operators or some finite linear combination of those. And so that's kind of the heart of what's called the amplification method interpreted geometrically. So this is following the works of Duke, Friedlander, and Ivanich in the 90s, and also the soup norm paper of Ivanich and Sarnak. And so that lets you do things like, for example, replace an integral like this with a modification where the modifying factor might be, maybe I'll square it here, some short sum of arbitrary coefficients weighting small integers raised to some power involving the integration variable. And so this weighting device, by choosing the coefficients in a particular way, say choosing them to be exactly L to the IT for some specific value of t, allows you to perturb this sum. And so that's actually where one gets a non-trivial savings in this kind of argument. And so all these kind of come from this basic idea of varying this test vector. Okay, and so I think that's all I wanted to say just about GL1. But yeah, are there any questions about this so far? Yeah, I don't remember too much one-by-one linear algebra in your course. I think you kind of, I mean, that was a little bit rough the first 3 weeks, trying to kind of catch up to everybody else who was already kind of proficient at that. But yeah. Okay. Okay, so then how about the story for higher degree L functions? Okay, so the setting that I like to consider, and so I'll consider L, so a higher degree L function, it's a function that generalizes the zeta function, and it looks like something like the zeta function to the nth power, but allowing shifts at each prime in each of the factors. And so we'll consider this, we'll use this notation to refer to so what's called the standard L function. Attached to some, so I'll focus on the case of level 1 automorphic forms. So pi will be some space of functions on GLNR mod GLNZ that transforms irreducibly in a certain sense. And so one thing one can attach to this set is, to this representation, is its set of Archimedean parameters that we'll call T1 through Tn. Okay, so then there's the analytic conductor that one can attach to this. So this was a notion introduced by Ivanich and Sarnak in a survey paper. Okay, and so this is a quantity. So these are the numbers that appear in the shifts in the gamma factors that go into the functional equation for L. And kind of for the same reason as for the zeta function, this quantity controls many natural features of these more general L functions, such as the density of zeros, and also the bounds that one can obtain for these things. So one desires, in general, a subconvex bound for these quantities, which is an estimate that looks like this. So you like to bound the central value by some multiple of some smaller power of the conductor than the fourth power, with the case delta equals 0 being the comparatively trivial estimate. Okay, so we should say something about why one might care to try to do this. So, I mean, I guess for the zeta function, I don't know Hardy and Littlewood's original motivation, but you know, maybe they saw proving estimates of this nature is some kind of very, very, very incremental progress towards the Riemann hypothesis, because of course that implies that you can take any number here, any positive number. But okay, more generally, so why care to bound L of pi half? So I mean, this is a very long story that kind of blew up in the 80s and 90s. So I guess the late 80s, there was the work of Ivanic and Duke Schulz-Pillow, and Walsperger kind of making the connection to L functions. So it says in some cases, so for a certain degree 2L functions, that problems like this control the distribution of things like the number of ways to write n as, say, a sum of 3 squares as n goes to infinity. And so that's a whole story that motivated a lot of the work, in particular some of the work of Michel and Venkatesh and predecessors to their work. And then I guess starting in the 90s, so Sarnak and company, Sarnak, and then there's a paper of Rudnick, Sarnak, and Watson's thesis, I guess in 2002. So they made this connection concerning arithmetic quantum unique ergodicity, which I'll describe on the middle board very briefly. So the question there concerns, for example, modular forms of the sort we were considering on this middle board. So let's say phi is, for instance, a Moss form on SL2Z. And so I guess it has some eigenvalue. So maybe eigenvalue a quarter plus, say, t squared. So I guess you can take phi, and if you L2 normalize it, you can define a probability measure attached to this. And so the question arose, what limits these measures would tend to as the parameter t increases. And so this is the question of AQE. And so what some of these works, and in particular, I guess Watson's thesis in this generality, established was that this was closely related to establishing non-trivial bounds for well, a particular L function attached to phi. So I mean, if you're not familiar with L functions in automorphic forms, just think of this as a bunch of symbols that allow you to apply the definition on the left board. And so here, psi is some fixed, say, Moss form on SL2Z. And I guess I should emphasize also that, you know, I'm considering Hecke Moss forms. Yeah. So, okay, so this is an example of an L function. And of course, to understand what the trivial bound looks like, we should think a little bit about what the Archimedean parameters are. So in this case, the parameters happen to be, so you get 2t. Well, I mean, let's say kind of what the parameters of phi are. So these are t and negative t. The parameters of psi, so since psi is fixed, we'll just think of those as being essentially 0. So you get 2 of them. And then the rule for forming the parameters of these is you kind of take symmetric combinations in a certain sense. So what they'll end up looking like is you get a set like this, and then each gets repeated with multiplicity 2. Okay, so this is an example where the conductor grows something like t to the quarter. Okay. Okay, so I guess this link established an interesting connection between a natural problem concerning the distribution of mass of these mass forms and some bounds for these L functions. And so as history unfolded, so I guess so Alan Lindenstrass made some important breakthroughs that resolved the conjecture. So I guess in the case I've indicated here, with some follow-up work by Sound. But I guess the conjecture is still not known in kind of the stronger form that's expected, where one can quantify the equidistribution relative to a negative power of the parameter t. So in particular, this is an example of a family of L functions where, in general, there's no subconvex bound known, except, so of course, I mean, before all this work, I think this paper came out in 2004 maybe. So Peter showed a subconvex bound for the above. So assuming a condition on phi, so assuming that phi is dihedral, which is kind of a condition that picks out a very thin subset. So in this particular example, not a very interesting subset, but you could allow congruent subgroups, for example. And it's a situation where you kind of avoid this kind of picture where the parameters are all of different sizes. So some are of size t and some are of size 0. Okay, so with a little bit of that kind of motivation, I thought we might now kind of summarize what actually is known more generally about bounds for L functions in higher degree. But are there any questions just on what I've said so far? Okay, let's see. Yeah, maybe I'll use here. So, okay, yeah, question. When is subconvexity now known? So continuing to restrict, as we indicated on the left, in the case of forms of level 1. So, there's been a huge amount of work on this, I guess going back over a century now. And I mean, if we don't care about the particular exponent that is saved, there are kind of now 2 results that sort of subsume a lot of that progress and organize it in a way that we can then kind of think, all right, what do we know? What do we need to try to understand moving forward? So one of them is this paper of Michel and Venkatesh that I've already mentioned that treats the cases n equal 1 and n equal 2 in generality. So under no conditions, it's known. And so the other is, so I have a preprint that came out in 2021 that treats the case. So okay, the new part is treating cases where n is bigger than 3 and maybe to some extent 4. So assuming a kind of critical condition on the parameters t1 through tn. So it's assuming the condition that, well, I'll say it in words. The condition is that each of the tj's is roughly of the same size as all of the other ti's, tj's, whatever you want to call them. So the way that I like to express that is we say that each tj is asymptotically comparable to some, say, reference parameter capital T that we'll think of as tending to infinity. Okay. So of course this leaves open cases like in this example here, where you have some parameters that are of size lowercase 2t, tending to infinity, and then some parameters that are of size roughly 0. So the result doesn't cover those cases. And of course, because the number of parameters here is, well, it's 3 if we don't double it, and if we double it, it's 6. It's not covered by either of these results. So maybe we should ask, though, like, why is it that the methods that kind of went into proving these results don't actually work? Yeah, sure. No. So in this particular paper, there's a bound on the level that is the square of the convexity bound that I gave. And then there have been some follow-up papers that kind of refine that. Okay, so in this paper, there are basically two methods that kind of come into play. So one is what we already kind of explained earlier in the talk. It's this this trick of taking a fixed vector, translating it, using that to get a weighted moment, and then, okay, I guess additionally amplifying in the spirit of Duke, Friedlander, and Ivanich. Okay. And then I ran out of room up there, so maybe I'll add down here. So the other method in this paper, so I'll explain it here. So you can think of it as a generalization, or I mean, it's a fourth moment bound for L functions on GL2. So it's a method that kind of, I guess I think if you trace back to papers that did it in a different language, it was first done by Duke, Friedlander, and Ivanich in, I think, the 7th paper in their series. Okay, they had some earlier papers doing kind of related things as well. So that was in the 90s. And then, so I guess the general, or I should say the kind of geometric interpretation of this was in actually Venkatesh's sparse equidistribution paper that came out a bit later. So that's what I'll kind of briefly indicate here. So in the same way that the first part of the talk worked with an integral representation for GL2 containing GL1, this method kind of relies on the theory of what are called triple product integrals for GL2. So if we take phi1 and phi2 to be, so let's take these again to be Eisenstein series, as in the very beginning of the talk with trivial parameters. And yeah, let's say we take phi to be some general, let's say it's a cusp form because we're working on GL2. So then what this theory gives is an integral representation where you take phi1 times phi2 times phi. You integrate that all over the appropriate quotient, so let's say PGL2. And this gives you something like the L function of phi raised to the fourth power. So it's a situation where you can again imagine trying to use some device like Parseval's identity to understand a moment. Sorry, this is the second power, I just noticed. Yeah. So you can imagine understanding a second moment of this over phi by applying Parseval's identity. So to give an illustration of how that works, so let's further stipulate that phi1 and phi2 have level 1, and then that phi is kind of a new form of level p. This is the situation that Akshay treated in his paper. So in that case, I mean, there's in general a modification factor that needs to be inserted here to make this identity exact, so kind of the analog of the gamma factors that we saw earlier in the talk. And in this case, it turns out if you don't modify the integral at all, it's easy to see from new form theory that you get a vanishing integral. But if you modify it a bit by translating one of the two Eisenstein factors by a diagonal matrix, so let's interpret this adelically, then you get basically this together with a fudge factor of size p to the negative half, roughly. Let's say it's asymptotic too. Okay, and then I'm finding I really like these middle boards. So I guess what this buys you is then that an integral over PGL2 of, so let's say phi1 of g, so you can write it a couple ways, but I'll collect the phi1 and the phi2s. So this integral is now somehow a proxy for a moment over phi of level p, so where we take the fourth power of the L function for phi. And on the other hand, everything on the left-hand side is fixed, except for this acting element A of p. So it's a situation where you can imagine using techniques concerning mixing or equidistribution to establish some kind of asymptotic formula for this. So in fact, the kind of mixing property of right translation by A of p says that this converges to something very simple, so just the products of the norms of phi1 and phi2. And then for kind of the same reasons as in this GL2, GL1 situation, so you can take all but one term on the right-hand side, and just bound this from below by that term. So this will give an upper bound here that'll kind of exactly match the convexity bound. And then you can vary phi1 and phi2 a little bit further. So this is kind of Akshay's geometric interpretation of amplification here to get a non-trivial bound for the right-hand side. So it's kind of a very, very similar situation to what we had before. So maybe we should say we're kind of thinking of it as related to this containment of groups, and in much the same way that the earlier discussion concerned GL2 containing GL1. Okay, so why does this not, I mean, okay, maybe I'll just mention one other thing, which is that, I mean, in the full implementation of this, where one treats more general configurations than just, say, some formal level P, where maybe you also allow non-trivial central characters, there's an interesting feature where it's not necessarily the mixing that is responsible for convergence, but rather a subconvex bound involving things of lower degree, so kind of involving GL1 that plays a critical role. So this is a 15-year-old paper where they noted this interesting kind of inductive structure in proofs of subconvexity bounds, which, so I noted another such example in a paper something like 7 years ago, and I don't know of any others, but it's kind of an interesting question whether there might be more. Sorry, what's that? It was this equidistribution reduction to Eisenstein observables for QE in the level aspect. So it was showing that if you knew a subconvex bound for the symmetric square L function, then you would also know the same for cuspidal twists of the symmetric square. Which unfortunately we don't seem to, but okay, it's still an implication. Okay, so yeah, so there's kind of a representation theoretic feature that plays a role in, I don't want to say producing, but identities like this don't seem to exist beyond the setting of GL2. So this seems to be kind of a special integral representation. And so this particular method doesn't seem to apply to any other group. So for example, to GL3. But okay, nevertheless, this method is sufficient to get a subconvex bound on GL2 in general. And as you can see, there are kind of two very, very simple and robust approaches. So the one that I've indicated here and the one that came from Peter's fourth moment paper that we indicated earlier that combined give the degree 1 and 2 cases in general. Okay, so then, so there's the question of the methods so the paper I cited of myself from 2021 giving this bound for n greater than or equal to 3. So the basic method involves trying to understand a sum over pi in some, what I'll call short family. So pi here is on, let's say, GLNZ. And it's a question of understanding the 2 n minus first moment of this in that short family and trying to prove an asymptotic formula for this using the theory of integral representations for the inclusion of groups, so GLN minus 1 inside GLN. And so if you go back kind of, in time, so I guess the case where n is 2 of this result, or in fact of the whole method, it's very closely related. It's essentially equivalent to what's in the paper of Ivanic and Sarnak on the soup norm problem. So it was sometime in the 90s. And then also there's an earlier paper of Ivanic on kind of the spectral growth of automorphic forms. And so maybe it's not obvious, in fact, how to kind of unify these two papers and understand them using integral representations. So there's a paper by myself and Akshay Venkatesh that kind of gave a way to map out a representation of, for example, a real reductive group analytically in terms of the cogent orbit attached to the representation. So this gave a different way to produce vectors than what we saw in the previous two examples, where we just kind of took some fixed vectors and translated them around. Here we're producing them in a slightly more complicated way, which is kind of needed to interpret this suitably. But okay, and then yeah, for n equal 3, this was done by Blummer and Butkin, but kind of rather than using integral representations, using more like raw analytic number theory ingenuity to quite amazingly produce this asymptotic without using the group structure in kind of an essential way. And then there are various papers. There's a paper of Simon Marshall doing this, or doing something like this, but for kind of, well, GLN minus 1, or its unitary analog, assuming some kind of very general position condition. And then I had an earlier paper as well doing something with somewhat less general position. In any event, all these papers have kind of been specific to the case that the conductor is large, namely all the parameters of similar size. And the reason for that is just that short families, so their size in this situation is something like t to the n minus 1 over 2. This is kind of the size of the smallest reasonable family, where reasonable means something for which you can even, for example, count the number of automorphic forms in them. So that's not something that one can kind of shrink any further. And when the conductor is much smaller, there's kind of no possible way that a moment of this degree can be useful for producing a non-trivial bound. You just end up getting worse than the trivial bound from this method. So, okay, we've seen some number of examples of moments of L functions that one can study using integral representations, and then try to evaluate asymptotically, and then maybe with a bit of amplification, used to produce a bound for an individual L function. And okay, I'm not giving a complete survey on all of the methods available to produce subconvex bounds, but I've kind of briefly indicated 3. So one that came from Peter's fourth moment paper, another that came from, I would say, DFI classically, and then Akshay's geometrization of that. And then this other line of work that kind of goes back to the papers of Ivanic, Sarnak, and Ivanic. And yeah, none of them seem to quite directly work in these higher degree cases. So yeah, and are there any questions about what we've said so far? Just, yeah.
It has Ivanic Sarnak paper. It has lower limit sums of moments of L functions.
Okay, that's a good question. So what they consider is a sum over phi in a family of, for example, phi of the imaginary unit I squared. And so this you can understand as like a base change L function attached to phi. And if you then kind of unsplit the whole situation, you'll get a second moment of its L function. So So indeed, they're kind of applying their technique more generally, not just to periods that represent L functions, but to any point evaluation. But yeah. Yeah.
At the beginning, you were looking at integral now you look at value at 1R. How might it be integrated?
So the way to kind of reconcile those is to think of the shift in t as being part of pi.
You allow that.
Yeah, we allow, I mean, pi is on GLN, so you can twist to kind of incorporate that. Okay, so then, yeah, if there are no other questions, I'll close by mentioning some kind of ongoing joint work with Subajit Jana, which we don't have in good enough shape to kind of say anything, particularly definite. And we have a very modest aim here. Our aim is to basically give a new proof of the trivial bound in generality. And then we'll see what we can do with that as we go forward. So, and the kind of idea is to go back to the very beginning of today's talk, take this argument involving translating something on GL2 and GL1, and try to find a useful higher rank generalization of that. So when I say useful, I mean, so when I kind of got into the subject, 10 or 15 years ago, kind of one of the first things you try when looking at higher rank is you say, okay, let's replace GL2, GL1 with, I don't know, GLN plus 1 GLN and start translating something around and see what we get. And so as Akshay kind of explained to me when I met with him to begin our project, you don't really get useful families of vectors in this way. They're kind of too big relative to the size of the moment in order to do something. So, okay, well, anyway, what we're trying to do is we're trying to use integral representations for GL2n and GLN to study, so a sum over all pi on GLNZ with conductor, analytic conductor up to Q. And as you pointed out, I should really write integral here because it's kind of a continuous family, but you could take one spaced elements, for example. So okay, of the 4nth power of this L function, okay, so and it's a family of size roughly q to the negative or q to the n. So we'll kind of weight this sum by the reciprocal quantity, so it's like an average. And okay, so after kind of modifying this a bit, maybe using an approximate functional equation, focusing on the main dyadic range. So what we've observed that was kind of surprising to us, I didn't know it until a few months ago. I'd be happy if someone told me that they had kind of come across this, is that there actually is an integral representation that picks off this family that just involves pure translation rather than something more complicated involving, say, orbit method and kind of microlocalization and defining a vector more directly. And we're not convinced that this is actually useful, so it's just kind of something we're going to see what we can do with. And what does it look like? So it's an integral over G in the quotient of GLN with determinant of size comparable to q to the negative n of, so a certain unipotent matrix that I'll call UQ applied to a certain projection of phi. So phi I'll take to be an Eisenstein series on GL2n. Okay, and that's it. And I just need to say what UQ and P phi are. So UQ, for example, when n is 2, looks like this. And so in general, it's just a matrix with kind of one interesting entry just above the lower n by n block. And then P phi, if you know the theory of integral representations of automorphic forms, is the standard thing that kind of appears. So it's a projection down to the mirrorbolic subgroup Pn plus 1. So I'll write it if anyone's interested. And I forgot to mention the linear algebra thing because I was so nervous and so focused and trying not to mess up other things in my talk. But I mean, kind of a fun pastime for me over the past years has been to count how many linear algebra problems from Peter's exams showed up in my papers. And so for the particular one here, the count rose to 4. And I really enjoyed these exams. I mean, they were kind of like a big spark for me because at the time when I looked at them, so I was deciding between like math, physics, computer science, and all these things. And I saw all these problems that seemed to have nothing to do with linear algebra. And, you know, I was like, okay, I don't know why he's teaching us these random things. And then sure enough, over my career, you know, somehow each of them comes back to haunt me. And, okay. So, all right, with that, yeah, thank you.
In this family, you get level off on average, basically what you're saying.
So I'm saying that if we succeed in doing what we want to do, which we kind of think we'll be able to, but have not done, then yeah, we'll get Lindelof on average here. And it's exactly a convexity critical situation. That's the idea.
Getting advantages, all the parameters having to be the same size, is that?
Yeah, there's no issue at all with that. It's kind of, I mean, if there is like a proof in the book of subconvexity, I think this has to be it. But yeah, we'll see what happens.
For these high moments, could you get an arithmetic formula? Or?
So the aim here is indeed, well, okay, you're asking for the literal moment rather than, I mean, I kind of lied here. So we're not even thinking about that refinement because we haven't even gotten an asymptotic for kind of the part that you get by focusing on the main dyadic range in the approximate functional equation. Experience suggests that, yeah, maybe. I mean, there's kind of no like hard reason why one shouldn't, but yeah.
So maybe shallow question. So what about the third movement? So is it just a leg of approach? Why do you talk about fourth movement particularly?
Oh, you're asking why do you consider even moments? I mean, you can write down an even moment by taking the quantity and multiplying it by itself or its conjugate. But you can't do that for an odd moment. Oh, sorry, unless you mean an unsigned odd moment, in which case, I mean, people think about these things. I mean, people have studied third moments for families of L functions that are non-negative, for example. That is something people do. And the talk was incomplete in that sense. Yeah.
The Eisenstein series here is attached to what physical data?
Everything trivial is kind of the intention, yeah.